taking into account self-interactions, or rather I should say, interactions with yourself or other particles in the form of self-energy loops, which continue forever, basically. Okay, so that you can't shut off those interactions, that's the subtlety, and we wanted to see how that changes the formula for deriving the S matrix, starting from a Green's function, which is to say, starting from calculating something like this. Some sort of a scattering where you had 3 particles scattering to. And if you think of these as places in space-time, these are very early and these are very late, but you can then Fourier transform those and talk about meta coming in. Now, just to see how we are supposed to slice and dice this in order to pull out the S matrix, we look again at this thing called the efficiency for a source coupled to this scalar, to this field operator. What is the efficiency for the field operator to act on the vacuum and create some particle, one particle state, okay, with some momentum. So we would like to know what that is. And so let us, so this is a kind of, you should think of this mentally as some sort of efficiency with some particular normalization of phi, act on the vacuum and actually have the amplitude to create state. So we study this thing, the 2-point function, Fourier transform. And that is equal to I, some Z, what do we call it? Z whole. Now, to diagnose what this is so for P naught positive, this is I over P naught minus omega P physical. And then Z whole over 2. So let's just ask why we are taking these various approximations and why we're taking this condition. Okay. This is the general 2-point function, and you'd have a copy of this in writing that like. Sorry. This is the dressed propagator, okay, including loop corrections and all that. And you can see there it's being used again and again in order to just write down the rest of this diagram to calculate this thing. I need copies of this. Okay? And so it definitely is, factors like this are definitely appearing here. There's no question. But the fact that we are taking the long time asymptotics of all of these points tells us that we better look at the on-shell approximation. So that's one thing we've seen. Now the second thing, the fact that I'm looking, for example, so I'm going to consider momenta in which, let's say I point this way. this, when I Fourier transform, then I'm considering positive energy going forward in time. So the fact that I'm considering this to be a large positive time, a very large positive time, tells me that in fact I would not just be sitting on the pole, I'll actually be sitting, I mean there are two poles sitting in here in energy. I'm sitting on the positive energy pole. I'm sitting very close to the positive energy pole. Okay, both of these statements. And so all these propagators oriented the way I've drawn the arrows so that this is P4. So let's just make it simple. P4 is an outgoing momentum, P1 is an incoming momentum. And that says that sitting, you know, you can do this all in the position space if you want. But as you're doing the Fourier transform, to get to a position space expression, this is sitting under some integral over momenta, and these are the momenta that dominate. The on-shell momenta for positive energy, that's what dominates the long time asymptosis. Okay? So that's why we're looking at that. And now you can see what this is. This guy is nothing but, the Fourier transform of this is nothing but e to the minus I omega p, whatever the time difference is that you're looking at between whatever your last interaction point was and T7. Okay, this thing has a simple Fourier transform, and recall, if you do the contour integral of P0, with the I epsilon prescription, this is what you get, step function. It says positive time evolution, and it's just this. Okay, so this is, and of course everybody knows what I mean by this symbol. Omega physical is just defined to be the square root of P squared plus M squared physical, which is the location of the true pole of the propagator. Okay. So it looks like we can see that there are factors here which are just taking, after the last interaction, it's just saying propagate the free particle forward in time. Okay? This is not something you want to include in the S-matrix definition. You could, but you'd be sort of, it's silly, because it's sort of a pure one particle, one free particle kinematic expression. So, as in tree level, we throw this away. We don't call it part of the scattering amplitude. This is what happens after the scattering. Or, if it's corresponding to one of these factors, it's what happened before the scattering. To get to the location or to get out of this location is just this factor. So that's not what we usually mean. So that factor we want to remove such factors from this entire expression in order to zoom in on the scattering amplitude. This thing is just going to be automatically 1 if we have done it right. That is, these 1, 2, 3 are truly early points, and these 4, 5, 6, 7 are late points. So that's that. In some sense, you'd like to throw that away. This thing here, this, remember, square root of 2 omega, is just that relativistic normalization of states factor. Again, a kind of a triviality. You're used to seeing it, even in the tree level scattering amplitude. And you're used to chucking it out, except instead of being omega with the tree level mass or the Lagrangian mass term, it's just the physical mass term. But again, nothing could be simpler, so that's not the issue. And then there's this factor here. Okay, so this is all that we're really worrying about at the level of loops in this discussion. And that we see, so just like a square root of this goes with one of the phi's, right? One particle with momentum p, right? A root z goes in there as well. So this thing is proportional. I'm not going to keep this kinematic factor. You know what to do with that. I've already forgotten myself. But basically, there's a root z pole. Okay. So So when we diagnose this, and we see that all this is, for long times, is just propagating a free particle, but of course, at one end, the first thing that happens is you start with a vacuum, then this thing has some amplitude to create one particle, that one particle propagates, and then the conjugate amplitude destroys the particle. That's the way you read this. Well, this is the so-called a kind of a wave function or normalization. It's saying that the amplitude to create one particle, whatever your usual canonical 1 over root 2 omega is, there's an extra factor of root z pole. Okay, so that's the meaning of that. And what we want to do, so what do we want to strip off from this? Okay, to get the S matrix, we want to strip off the root z pole for, and let me just say, 1 through 7. So for each of these external particles, 1 to 7, you see there's a root z there, root z there, root z there. All of these are just the efficiency of the gun, 1, 2, and 3. There may be different species of particles, and therefore they might have different interactions, and they might have different root z's. But there's an efficiency factor, root z, root z, root z, and in the detectors there's an efficiency, root z, root z, root z. That's the business of the guy who builds the guns and the detectors. I want to know the intrinsic scattering amplitude once I know that you've actually given me those particles. It's like conditional probability. I don't want to know how likely it is that you throw me a particle, but if you threw it, and all 3 of these guys threw it, I want to know what's the probability of, in this case, the probability amplitude for them to scatter. Okay, that's the simple point. And so we'd like to strip off a root z for each external line. Okay. But because, even though this can be a very complicated function of P, it's incredibly simple, close to on shell, which is to say, the thing that's relevant as I take these points in space-time to be far future and far past. It's incredibly simple. It looks just like a free field expression except for the root z, and so I'm telling you that the answer is incredibly simple too. Do whatever you were doing for the S matrix at tree level, except knock off an extra root z, divide by an extra root z factor for every external line, and evaluate all external lines on shell, but on physical shell. Okay? Right. So this fact here, right? Or if you want. Zooming in on that mass shell and stripping off this, that's the only 2 things that come in at loop low. That's it. So we can write the we can put it together and just write what the scattering amplitude is. It is equal to so you have some outgoing and I guess I should really call it IT, right? It's too silly to talk about the case where there's no scattering at all. So here's this scattering matrix is equal to the limit as you go as P's and K's on shell, which is to say P0 is positive, K0 I'm taking this limit and k squared why don't I just say equals? Well, I'm taking a limit because I'm trying to use these limiting behaviors. Now, so it's very much like what I would have said. I would have said some analogous thing except just m squared. I wouldn't have sweated this issue of what is the physical mass. But this would have just been like the tree level thing. And then, normally we would have written this Green's function. So here, let me write a math expression instead. A picture. Okay, something where the machine can calculate the correlation function. And then let's divide it by the So when I write it like this, I just mean do the Fourier transform of this and write it in momentum space. That's all I'm saying. Just do the Fourier transform, write it in momentum space. But then product over I root zi product over j root zj. So this is outgoing, incoming. Okay, so this is the formula for the S matrix element. Let's just check what I do there. Here I said strip off a root z. I said strip it off. Here I seem to be multiplying by root z's. That's because the propagators, all in the denominators there, have a whole power of z. So if you like, there's a root z divided by z. So that in net, I'm actually dividing by root z. Okay? So make your peace with this. But if you want to think of it as just diagrammatically, then it's just product over I, root zi over for particle I, product over j, root zj over j, and then okay, so you just draw the Feynman diagrams for this thing. You throw away these external propagators, dress propagators, except for a root z. So these propagators already contain a z, and a root z of it is all that you in net divide by a root z. And then you take the limit as you go on shell, and you go on shell physically. Okay, that's the crucial thing. And that's it. functions from correlation functions. This business of, so this is sometimes just drawn as so this business of lopping off, taking off these external dress propagators and going on shell. I think the better way to say it is, let's continue to take a limit. So let's use the word amputate to mean just throwing away these external propagators, the external dress propagators. Okay. And so we can even continue to write the product of I through Zi. So let me use the definition that amputate just means throwing those things away, or if you want, dividing by them, so they go away. But then on top of that, you have to do this, the instruction there, and take the limit, the same limit that we're talking about. So it's a useful language to just say the word amputate. Partly because clearly calculating the amputated thing to go to the unamputated thing, even if you wanted it, would just be to be multiplying by the dress propagators. It's not a very complicated operation, it's just multiplication. So it's useful to talk about the hard question. The hard question is, what's this? And what is this separately? Multiplying them together is easy. You might say, gosh, it's not that hard. All you have to do is write this. But of course, it is hard, because you have to know what that is. Okay, so to do this. Okay, I mean, you have to do a loop computation. Now you do this to whatever order you want to work to. So you want to work to one loop order, do dress propagators to one loop order, and do scattering processes to one loop order. And that's it. Okay.
The efficiency, the Z's, are they measured? Is that what we're talking about here? I mean, we can't find those out. We can't calculate them.
Yeah, we can't. So once if you like, once I give you a set. So once I give you a set of fields with some choice of normalization, and so for example, suppose I give you a dress propagator. Let me just start there. Suppose I give you a dress propagator that looks like this. We're normalized, but minus some signal p squared. By some process of renormalization and calculation, you figure out that this is the dress propagator. And with this being the dress propagator, you have some Feynman rules for gluing these together to get with some interactions, to get a beyond 2-point correlation function. Okay. Or Green's function. Then, once I've calculated it in this language, this thing is equal to a I z whole over p squared minus m squared physical plus I epsilon. Okay? We can hunt for the pole of this propagator perturbatively, if necessary, and you can write it like this. So, when it's nearly on shell, it contains this pole. Okay? Now, that z is calculable. If I said, in fact, we can do it right now. We could just say, I want to find out where this thing is 0. actually did it. If you go back in your notes, you'll see a place where I say, how do you find a pole like this? I'll show you how to do it perturbatively. And there's a unique answer. And you could write it in this form. And I'm saying, once you've got it in this form, that's the Z I'm talking about. So yes, if I give you some scheme in which you calculated this, then there really is a calculation of this that you do, and it goes in there. Okay. Now this might make a little more sense when you do the homework, because where it comes in, you'll see it comes into actually doing some sort of a scattering, which we haven't really done yet, but in the homework you will. And remember, the homework got delayed by a week. But we'll see how that plays out in a simple example. Yeah.
So every now and then you refer to Z as kind of something you can think of as an efficiency for your particle production. So is there a way in which you can think of moving these factors of Z onto the interaction?
Yes. And you'll see this is exactly something that comes up in the homework. Because clearly you can redefine what you're calling phi. You call something phi, I'll call my phi twice rho phi. And, but then in interactions, you know, if I write phi to the fourth, if this is your interaction term in the Hamiltonian, Hn, and I define mine to be yours times 2, then I can certainly write that. This is some of the arbitrariness in the language. But then I'll have to have lambda, I'm already lost,
16.
over 16, over 16. Yeah. Whatever, you get it, okay? So, yes, this will come up. But what I want, you see, there's this vague sense, and I can stand up here and say it in many different ways. There's this vague sense that there's some shifting ground. The ground is shifting under you. Because there's some part of this which is convention. Some part better be some piece of physics, like something like an experimental split plot, C, okay? So the idea of doing the homework is to do the simplest examples where you actually see, oh, right, so there I got something solid. But I can see where all the arbitrary, freedom is in my choice of words and symbols and definitions and so on. I'd rather you work through a case, puzzle it out yourselves, think about it in your own language. But I think there's enough there, and enough in what I'm saying right now, that you can put it together, and then I think you'll at least see, just in the simplest case, that there's both something invariant and physical, and there's something totally conventional, and you'll see the difference. Okay? Okay, now, that was the... In fact, so it's worth saying. So just one more thing about, we'll talk more about this later, but while I'm going through all things self-energy, let me talk about this notion of an on-shell renormalization scheme. So, this sort of dressed propagator renormalized, that is written in terms of the renormalized variables, we said you could write it perhaps like this. So when I showed you, I've separated the issues of getting the S matrix from the issue of just getting something finite, so that we can even talk about getting an S matrix, just getting something finite. So when we got something finite, when we got something finite, I just showed it to you in this language. In fact, there was a sort of a Z at some point here, if you want the renormalized Z, but I just chose it to be 1. If you go back and look, I could have just done this and said, I can just choose this thing to be some finite result. This is finite. Okay. But these are, of course, if I wrote them in terms of my original wave function and my original mass, they are ultraviolet dependent quantities, right? That's why we took them as inputs rather than outputs. So if we're staring at this, then there's one way of parameterizing the theory, which is to just tell me these two numbers. And of course, really, you should be telling me G, and you should be telling the mass of the fermion. So you have to give me a handful of inputs, and then I'll calculate everything. Indeed, you can sort of see, if this is just pure fluff, just convention, why can't I just choose a convention in which z pole is 1? I think some part of some of your questions is, why do I have to calculate it if I can just set it to 1 and be done with it? Okay. So indeed, you can try and say, so this is a general normalization scheme. Okay, so I just want you to get back in your minds to when we had this expression. Why do I call it a general renormalization scheme? Because you'll remember that one of your questions was, if this is finite and this thing if this thing contains the divergences and this thing is finite, if you want, it's this thing I call tilde, or if you want, the normalized guy. Everything here is finite. There was some arbitrariness in how much you could always take some finite piece of this and put it here. That was an arbitrariness. And so I said, well, how you do it is your choice. You know, if you want to take 3gv squared out of here and put it here, go ahead. That's an equally good choice. Okay. The sum of the two is the physical thing that we are going to care about, but you can shift something here and shove it there. And that would just define a different m squared renormalization. So you could have m squared renormalization prime is defined to be m squared renormalization minus some constant k, and then sigma tilde renormalized p squared. In fact, we can make it a function of p. Is, oh no, you can't, because I'll call it vectors in this case. And this is m prime sigma normalized p squared plus k. So we know that there is this sloppiness to it. So I'm saying, in some scheme, I've chosen it this way. I've chosen the separation of what sits here and what sits here and what sits here. I've chosen it in some way, and I'm writing this expression. Okay, so that's what I mean by in some renorm, if you want, I could say, in some renormalization scheme. Imagine that we start in some renormalization scheme. Okay. Of course, there is an arbitrariness. That's what I'm pointing out. So I'm just reminding you why I'm even bothering to say the word in some scheme. So the on-shell scheme applied to self-energy chooses Z renormalized is to choose G dressed renormalized or P squared near M squared physical to be I P squared minus looking propagator, except this is m-physical. But the z-pole is just one. This is what everybody here would like me to say. Okay, so there is a scheme in which you can demand this. M squared renormalized is nothing but m squared physical. How many different m squareds do you want? Why can't we just have one new m squared? Why can't I just take my renormalized m squared to be my m squared physical? Now it turns out that these two conditions, this and this, are secretly telling you how much to shift of this into here and how much to rescale your fields and so on in order to make this happen. So if you want this very pretty looking formula, which has the fewest moving parts, and everything just looks like tree level except the physical mass shows up there. It's not true everywhere, by the way, it's crucial. This G dressed is not this simple. It's only this simple nearly on shell. But if you want the best you can do to make things look as close to tree level as possible, at least when you're nearly on shell, well, that's a choice of scheme. And you could ask, why wouldn't I do that? Well, there are many processes in which you need the propagator off shell. So, for example, here's a diagram, here's a dress propagator. Here's a process, maybe time is even going this way. Here's a process in which this line is not on shell. So, there's no particularly great significance or savings by demanding this. But there are other situations where it is useful. So it's your choice of scheme, and people choose schemes to suit the problem that they're interested in. But there is this kind of, what most beginners would think was the sort of self-evident, most physical scheme, which is the so-called on-shell schemes, and where you're basically trying to choose your renormalization scheme to fit, literally. The word on-shell is because of that, on-shell. And this is it. Now let's just see that it is a scheme in the sense that all it does is tell you how to redefine your field and how much of this to shove in here or move out from here to here in order to get this to happen. Okay? So right now, the general G dressed will, of course, for p squared near the pole, will look like IZ pole over p squared minus m physical squared plus I. We already know that this thing can be put in this form because it does have a simple pole in perturbation theory. We've discussed how to find it in perturbation theory. So definitely it has this form when it's nearly on shell, and clearly by rescaling Z normalized, Z pole can be set to 1. Okay. G dressed is proportional to Z renormalized. If whatever choice of Z renormalized you had in this general scheme was not giving you Z pole equals 1, just rescale it and then it'll give you Z pole equals 1. So if you want, what is the exact rescaling? Is Z renormalized. Obviously. Okay. So that one was easy. But what about so therefore let's consider let's focus on this other thing, m squared renormalization. So that means that the second condition is saying that p squared minus m squared renormalized minus sigma tilde p squared So if I'm hunting for the pole, m squared physical, I should look for the zero of this function. So that means, by definition of, so of course that pole position is m squared physical. So of course this is true. Right? That's how you would find m squared physical. And but that just means that, so this is true in general, but, and this is of course approximately m squared renormalized plus sigma tilde m squared renormalized, because the difference between these two is a higher order effect. Okay, so say at one loop, let me just, one loop precision, if I do it more loops, I'd have to do this more carefully, but at one loop precision, this is true. The condition m squared physical equals m squared renormalized, okay, just this. If you demand this, then it implies sigma tilde of m squared renormalized is equal to 0. Okay? So it tells you, but your original sigma tilde may not have that property. May not have that. But this is telling you exactly how much to move around in order to get it to happen. If you just, if this is not true, so we can achieve this just keep doing this until we hit that place. Okay? So then we're done. So you'll succeed. Okay? And that's a scheme. And sometimes that scheme is useful. The general thing, which I think we can't see here, I'm just going to assert it, but the general rule is this, that there are schemes which are handy for experimentalists, because tell them various other more abstract schemes and everybody gets confused. What I mean is that when experimentalists are correlating different channels, what they'd like are schemes totally optimized for the particular set of channels that they're correlating. All physics is about correlations of different experimental measurements. But a particular experimentalist might well be correlating 2 or 3 channels. That's it. They would like some scheme to be chosen to keep that correlation process as simple as possible, so that as many of the renormalized input parameters should actually be things that they directly measure. They don't want to have to measure it, and then they have to process it, and so on and so on. So, for example, if they measure, of course, they measure the physical mass of the particle. If that itself is one of the input parameters formally of the quantum field theory, they're happy. If they have to take this, and they have to solve some self-referential equation, this, that, and the other, and get this, then they hate it. So, on-shell schemes are often designed so that the input parameters, the renormalization parameters, the renormalized input parameters are as close to things that the experimentalist measures in those channels that you're optimizing for. And so then they can predict one of the things they measure, and then see whether the prediction worked or didn't work. Okay, that's it. However, we will see later that in general for theorists, by which I mean general purpose physicists. That is, we don't want to just optimize for 3 channels that happen to be of interest today. We might want to optimize for the most general process. I don't know what process is going to be interesting today or tomorrow, so I want a kind of a scheme that's sort of easy to use for theorists, and let the experimentalists work hard in correlating all the data. Okay, that's the way we'd like to work. So we have other things where we use regularizations that you may have heard of, like dimensional regularization, where we use schemes like minimal subtraction. These schemes don't have this property. Okay? The input parameter is a very highly abstract thing. No experimentalist can look at the input parameter and say, oh, it's just that measurement over there. Instead, this input parameter is the result of a fit to many channels. Because when I have 10 channels, and I have, say, 3 input parameters, those 3 input parameters, none of those 3 is like one. So here's the one. There are 10 measurements. 1, 2, 3. These are experiments, okay, or experimental channels. And there are input parameters, G1, G2, G3. Okay, and they're renormalized. If you tell me these, I'll predict these 10. Okay? But you don't tell me that. Well, I don't know what they are a priori. I'm just looking at these experiments. So what I have to do is instead fit. And the goodness of the fit will tell me whether I've actually got it, right? Within experimental error, these 10 things are fit by some choice of 3 parameters, then I'm good. It would be great if this was just equal to this, this, and this. Then you could phrase, if that were true, it would be great, because you would just measure this, that's G1, measure this, G2, measure this, G3. And then, using that, I would predict 4, 5, 6, 7, up to 10. Wouldn't that be lovely? If you can optimize like that, the renormalization conditions, so they literally match the results of experiments, that is the closest thing to an on-shell scheme. That's generally what we mean by on-shell schemes. But they're very linked, optimized to the set of the suite of experiments that you're doing. But if you don't know which set of experiments you're doing, then you need a kind of scheme that's sort of easy to use for theorists, because we're not taking the experimentalists into account. And then, what it turns out to be true is it's not like this. Instead, it's these 3 parameters fit to these 10 things, and this G is not any one of these things. Okay, so that's the game. Okay, there was a question. No. Okay, switching to the next use of self-energies. And that is the unstable particles. This is really magic, in my opinion. And it's sort of what, again, you get to see the magic of quantum mechanics and how it is hidden inside of these Feynman diagrams. So we're about to do self-energy, but for p squared bigger, or p squared of the scalar, well, p squared bigger than 4m squared. Where, remember, this is m sub. So we're still doing the self-energy diagram. And if you amputate this, this is what I mean by sigma, I'll put some factor of I. That's the self-energy diagram. So recall that the sigma is, I won't write down everything, but recall that it starts with this, right? Q dot P. So this is how we started the whole game before. But there's a problem. If you go back and look at your notes, you will see that when I did wick rotation, so of course there's plus or minus regulator diagrams. Okay. You can think in two ways in general. The sort of the hack way to think, which is very, as I said, evocative of what high energy physics can do, is to think in terms of regulator diagrams and to regulate things and think of the regulator as really the effect of UV physics that we don't know. Okay? The slick way to deal with this, which is, if you like, the way that makes it clear that no arbitrary nonsense is being put in by hand like this, is to just differentiate this until it converges. Manipulate it in all possible ways, do whatever you want to do, and then integrate it. Wherever you have integration constants, just fit them to the experiment. Okay, so in other words, they are secretly part of things like m squared normalized. There are two ways to do it. Okay. Yeah.
Is it easier to calculate using these regulators like that, or using the differentiation and then do the integral, or is it about the same? Or?
It's what turns out to be easiest is, so actually differentiating would be easier in general than using, for typical real world processes, than using some sort of Pauli-Villars regulator. That is a true statement. However, renormalization schemes like this, very on-shell things and so on, as I said, they're great if you know exactly the set of experiments you're about to spend 5 years on. But in general, not so great. And so we'd like the simplest renormalization scheme, the simplest algorithm for cutting off all the infinities, throwing them away, and not fretting about what we had done. And that turns out to be linked. That's called minimal subtraction. And that turns out to be linked, that the algorithm for what you do is very closely linked to a regulator. And that regulator is called dimensional regularization. And so in that case, that's the way practical work is done for most stuff. And there, the regularization and the renormalization scheme are so closely tied that you use the regulator. But in principle, you can do all sorts of practical work by just differentiating this enough times. But then you have to state what your scheme is for integrating and getting the integration constants. And if everybody else is using minimal subtraction, which is linked to dimensional regularization, you won't know what they're talking about. So it's at that level of practical convenience, but no in principle issue. These Pauli-Villars regulators, I'm calling them useful as being evocative because they seem to have a mass scale, lambda. You can sort of see how the cancellings are going and so on. And it's very true to the physical effects of ultraviolet physics in general, honest ultraviolet physics. So there's the hierarchy of ease. Easiest, dim reg, minimal subtraction. Next easiest, just differentiate until you can get something finite. Then Pauli-Villars, but conceptually, I'd go the other way. So it's nice to know because, as I said, half the problem in this game is knowing what to calculate, which is often because they're conceptually confused. So, check. Exercise. Check. That with p squared bigger than 4m squared, we can't straightforwardly wick rotate. So you will find that this thing where we had some Q0 integral to do, and we wanted to turn it into a kind of a Euclidean Q4. We did by taking Q0 like this and rotating it like this. This is what we did before, and then we got all the virtues of dealing with Euclidean space and stuff like that. However, check. You can use Lorentz invariant, so you can go to the center of mass forever. You can use a frame in which p vector is 0, for example. But check by any means you want that when you have poles that look like this, you cannot simply, you can calculate the effect of the pole, that's okay. But you cannot just trivially, like we did here, say, oh, right, it's just the same as doing that, because you're encircling a pole. Again.
I think I talked to you before.
Yeah.
Combined with Feynman integration tricks
Yeah.
with big rotations, we have safety, meaning
You
you always
still
can
do.
shift pole in that
That's
configuration
right, yeah.
so that we
And
can.
remind me, what did we say? We said that.
So basically here we have 2 simple poles right there.
Yeah.
Sorry. So 4 simple poles right there.
Yeah.
But if I apply Feynman tricks,
Right.
basically what I do is I'm making 2 separate poles, but just increasing the order of the degree of the pole itself. But in that sense, again, the configuration of the pole just look like that as well, so that it
I
is
see.
safe.
Right, right. So, good. What Sundrum was pointing out is that in the Feynman trick, instead of getting a product of poles,
Right.
which might end up in this situation and stop you from doing this, if you first use the Feynman trick, then you would get, the Feynman trick would have various x's and p's squares and things like that, but it would be the whole thing squared.
Right.
And so there'd be only one there would be a single pair of poles, but you're saying that we can shift the integral so that basically it looks like this.
Right. So basically we are merging different separate poles into higher degree poles, but in 2 separate positions right there. So that still we have safety to make rotation after that.
I think that's true, and even if we didn't do that, I think you can take into account using the contour integral these poles.
Right.
But the thing I wanted to point to, so you can be clever, there's no question. It's not that clever. I mean, no, of course it's clever. It's not ridiculous. I mean, you can just bulldoze your way through this and just calculate it, okay? There are many ways you can try and shift and push it around or calculate the effect of this thing. But actually I wanted to recycle. I don't want to do anything again. I just wanted to recycle